Hey students, I want to chit-chat for just a minute about electronegativity. Electronegativity is the ability of an atom to draw electrons to itself in a chemical bond. Another way to put that, it's the capacity of which atoms share electrons. So to get an idea of what's happening here, let's imagine that over here we have some atom A, okay? And over here we have some atom B. Here is A's nucleus, and here's B's nucleus, right? And remember, at the nucleus there are these protons that are attracting these shared electrons that we're going to put right here in the middle, right? So here is my shared pair of electrons, okay? And so I want you to imagine, if you can, that atom A, it has protons, and it is drawing these atoms to itself. B is doing the same thing as well, so let's draw what that might look like. So here's B, right? And the electrons, so these electrons are feeling the attractive forces between the nuclei of these two atoms. So let's say I was going to talk about the electronegativity of B. I'm referring to then just how big are these arrows right here. If they are super big, then I know that I'm talking about a highly electronegative atom. Now, in terms of electronegativity, every atom has an ability to attract electrons to itself. And so every atom has some amount of electronegativity. You could think of it that way. And so if you look at the graph on your screen, what you're looking at is a three-dimensional representation of a plot of electronegativity. And so this was done by Linus Pauling many years ago, but you can see on one region of your graph you've got a pretty high value, and on the other region you've got pretty low value. And this goes back to the fact that on the right side you've got high nuclear charge and small size. So Coulomb's law says that these electrons that are being shared are going to experience a greater force of attraction to the nucleus of these small atoms compared to that of the larger atoms. Now, where these numbers come from doesn't really matter, okay? And you certainly don't need to memorize these numbers, and if you ever did need them, they would be provided to you. But what we can do is some pretty nifty math with them. So one thing we could do is talk about the difference in electronegativity. So hopefully this symbol right here is one that you all are somewhat familiar with, that little delta symbol. Quick recap for you. If y'all remember, that delta symbol, maybe you've seen delta y over delta x in math class or something like that, right? Where the delta sign just means the change in something. So that's the change in y. So y2 minus y1 all over x2 minus x1. So this is the common way that students normally see the delta symbol, and that's exactly how that is exactly what I mean when I use that symbol as well. So that just means that the change in electronegativity, what we want to think about, or the way that we think about it, is we're just going to look at the magnitude of difference between the electronegativity of one atom in a chemical bond minus the other atom in the chemical bond. Okay, I use absolute value signs because I don't care about a negative value. So here's what Linus Pauling says. He makes a plot, a diagram. And on this diagram, he's going to say, okay, the change in electronegativity, it can be 0, and then it can be any number. And so what he did, though, was he was able to categorize a few things. Over here, we're going to put 0.5, and then way up here is 1.7. Again, these are two numbers you don't need to know. But what this is telling me is that if the change in electronegativity exists between 0 to 0.5, then that means then that this is what we're going to call a nonpolar covalent bond. So what do we call this region? We call this blue region a polar covalent bond. And finally, we call the red region an ionic bond. So how do we determine the change in electronegativity between two atoms in a bond? It's very simple. Suppose, students, that we had, for just a moment, the carbon to nitrogen bond. Let's take a look at its electronegativity. So looking at the scale on your screen, I can see that carbon has a value of 2.5 minus nitrogen's 3.1. It doesn't matter what order we write these numbers in. So 2.5 minus 3.1 is 0.6. So what that tells me then is that the carbon to nitrogen bond is a polar covalent bond. Let's try another one real quick. So let's say, students, that we had a carbon to hydrogen bond. So again, if we compute the change in electronegativity, this is going to be 2.5 again, minus 2.1. So we're going to get a value of 0.4. So looking again at the scale, I can see that this is going to be a nonpolar covalent bond. Sometimes we might refer to this as a pure covalent bond. So computing the change in electronegativity takes the guesswork out of determining whether or not a bond is polarized, non-polarized, or just flat ionic. So students, another way to think about electronegativity is to imagine a tug-of-war contest. So let's think of it in this respect. So we've got person A on our left in blue, and we've got person B on our right in green. You can see the midway point between them in red. So obviously we're going to have A pulling this direction. We're going to have B pulling this direction. So what's written in blue, what's the arrow in blue or the arrow in green? That's what electronegativity is. It's the force of attraction. It's their ability or their strength, these atoms, to draw or to pull on those electrons that are tying the two atoms together, just like this tug of war is tying both person A and person B together. So to kind of imagine this, here is my atom A, here is my covalent bond, here is my atom B. So if we were to look at the difference in electronegativity between these two atoms, let's say that it is less than 0.5. This is what we call a purely covalent bond. That means that if this is where we begin, then what does the end look like? It looks like this, right? There is no clear-cut winner whenever you have both atoms that are pretty much pulling on these electrons equally. So if going back to the tug-of-war analogy on your screen, that means that the end fight, there really isn't a whole lot of change. There might be some movement around, but not a whole lot. So let's look at another situation. Let's suppose, unlike our previous example, now we have someone a lot stronger. I'll say that A is very, very strong. This guy is strong. And over here we've got B, who's just a little guy. Okay? Really can't pull very hard. What do you think the end result in this tug of war is going to look like? Well, you guessed it. Obviously, A is going to win this tug of war contest. So what does that mean in terms of the actual bond? So going back, if we just imagine that we've got atom A, and we have atom B. If the change in electronegativity is somewhere between, say, 0.5 and, say, 1.7, then this is what we call a polar covalent bond. And what that means then is that if A is winning this tug-of-war contest, then we would say the electrons are going to be found more often on A. Okay? They're going to be on A more of the time. And so what we do to represent that is we're going to put a little lowercase Greek letter delta and then a little itty bitty minus right there. And what that means then is that atom A, has a slight negative charge, which means then if it has a slight negative charge because the electrons are on A more often than they are on B, then B would only have a slight positive charge. And so because of this reason right here, students, because A is stronger or more electronegative than B, then as a result, I hope you can see we have created a polarized or a dipole bond. Notice that we have di as in two poles of a magnet, like a negative and a positive end, north pole, south pole of a magnet. We've created the exact same phenomenon here in this bond of this atom A to B. And so this isn't like a ionic full negative bond or a anion full negative or a cation full positive. This is just only slightly negative or slightly positive due to the difference, the wide difference in how these atoms are sharing these electrons. Because poles of a magnet were created, we call this polarized, or another way stated, a polar covalent bond. Let's look at one more example, and in this example we're going to look at atom A, and this time atom A is going to be much more electronegative than B. In fact, B is just going to be this little, almost minuscule person, right? What happens in this case? See if you can guess before we go to the end. Unlike in previous examples where there was still sharing of electrons, here we don't. Here atom A completely stole the electrons right out of B's hand. In fact, B is no longer, it's no longer even pulling on these electrons, so to speak. Now it's just flat lost the electron that it once had. In this example, students, we're looking at a difference in electronegativity that is going to be greater than 1.7. Atom A, here's my atom B as before, but this time I'm not going to write a line between them because there is no sharing of electrons. Instead, what's happened is we've got atom A over here who has just flat taken the electron from B and has now gained a negative charge. B has just flat lost that electron, and so it is now positively charged. What attracts these two atoms together now is Coulombic forces, aka this cation is simply attracted to this anion. So in closing, we would call this bond the familiar ionic bond. So students, this is how we can use the difference or think about the differences in electronegativity and use those values to determine the type of bond we're looking at, whether it be a nonpolar, a polar, or an ionic bond.